So this week's just a review week. There wasn't really a lot to do this week. You haven't had any assignments at all, so this was a good week, and it still is for you to maybe start your information literacy paper. So just a reminder for that. Information literacy is due November 18th. So it is a 500-word paper. It can be in MLA format or APA format. It's really only going to be about 3 pages long, not including your reference page. So whatever format you choose, stick with that format. You do need a reference page. You do need 3 references, 1 from a book, 1 from an internet site, and then 1 from a periodical, so like a journal, a magazine, something like that. If you go to the UA-PTC library website, you can search for books, for journals, periodicals, and find all of those resources there. I'll post a link to the website, the library website, and there's a search bar that allows you to do that. So make sure that you're working on that. You can pick one of the topics that I have suggested on the handout that is in Blackboard. Or if you want a different topic, that's fine. Just email it to me and get it approved first. Okay, because it does need to be either chemistry, physics, astronomy, one of those areas. All right, so with that reminder, due on Sunday is going to be the exam for Chapter 5 and 6. And we finished covering Chapter 6 last week, so this week is just pure review week. There's no discussion, no homework, anything like that due this week. The only thing that's due is this exam, and it's due by Sunday. It will be up today. It's 40 questions. I believe I might be off by 5 questions or so. It's either 40 questions or less. I know it's not more than 40. And there is a 2-hour time limit, so you just get the 1 attempt. Now, it's probably 50-50 concepts and the other half actual calculations. So they're not all calculation problems. When you get ready to take the exam, have your equation sheet ready. Okay, I have one posted that has all the Chapter 5 and all the Chapter 6 equations on it. Do you guys need one of these, or do you already have one?
I already got one.
You have one too, Courtney? Okay. So what we're going to do today to review is I posted a practice exam, and I've noticed past practice exams, only about half the students actually do them. So I was just going to do it in the video, so that hopefully if you watch the video, you'll at least do it through me. So looking at the practice exam, this will be attached to the video, so if you're watching this virtually, you'll find this attachment with the YouTube video. So for number 1, all of the following is true about heat except. Okay, so when we talked about heat, heat was that Q value, and the equation that we have for heat is MC delta T. So why am I bringing up the equation when this is a concept question? It's because the equation can help us answer it. Okay? It's saying the choices are giving you, for instance, A, heat is dependent on the type of material. Okay, well this equation tells you what heat's dependent upon. So heat is dependent upon M, which is mass. It's dependent upon T, which is temperature. And this C value, that's specific heat. So it's dependent upon specific heat. And remember, when we looked at specific heat, originally in Chapter 5, we had a table that had a list of specific heats. And those specific heats were dependent upon the substance, the type of material. So specific heat is dependent upon the type of material. What's the material made of? What substance we're looking at. So you can use the equation to kind of help you with the concepts as well. So looking at this, which is true, all the following are true except, so we're looking for the one that's not true. So for A, is it dependent on the type of material?
Yes.
Yes, it is, because of specific heat. Is it dependent upon the amount of a substance? That would be yes, because mass is the amount of a substance, right? It's how much you're putting on the scale. So this is amount of a substance. So yes, it is dependent upon that as well. C C, heat is transferred from the colder to the hotter object. Well, the equation doesn't really help me with that, so let's skip that. That could possibly be the answer. Going down to D, transfer of heat is caused by a temperature difference. So is it caused by a temperature difference?
Yes.
Delta T is temperature difference. It is change in temperature. So by default, we would say C is the correct answer. But why? Well, when we have a heat transfer, heat's always transferred from the hotter object to the colder, right? If you're holding a cup of coffee in your hands feel warmer. Why? Because the coffee is the hotter object and it's transferring heat to your hands, which is the colder object. So C is the incorrect because it's saying it's transferred from colder to hotter. And that's just not true. It's from hotter to colder. And you'll see variations of these same questions on the exam. So make sure you're understanding these choices and concepts and equations that I'm going through. So for number 2, the energy required to turn a solid into a liquid. Okay, so an example, say we have an ice cube and it's melting to form a puddle of water. Okay, so this is a solid ice cube and this is liquid water. So the energy required to turn that ice cube from a solid into a liquid is known as what? So specific heat is dependent on the type of material it's used in the heat equation. Latent heat, yes, latent heat is the correct answer. So how do I know that? Because of the definition of latent heat. And this is something you would have got from the PowerPoints. We didn't talk about this in class because it's a concept. It wasn't in any of the equations. So latent heat is the heat required, this is word for word the definition, heat required for a phase change. And when we say phase change, solid to liquid or liquid to gas. Because what's happening when we have a phase change going from a solid to a liquid is that the temperature itself isn't changing, just the form is. So the heat going into the system, the heat melting this ice cube, isn't actually having a temperature change. So we can't measure it using this equation. That's why it's called latent heat. Another term for it, for latent heat, is hidden. It's hidden because you don't see a temperature change. So since we don't see a temperature change, we can't actually calculate it because the temperature change would be 0, making this Q value 0. All right, so the first several questions are all concept questions, but don't worry, we'll get into some calculations as well. Number 3, which form of heat transfer occurs when 2 objects involved are not touching? So we talked about 3 different types. We have conduction, convection, and radiation. What were the keys? Well, conduction, objects are touching and not moving. So that's the key here. Touching, not moving. And you can bet you'll probably see 2 to 4 questions talking just about these. Okay, so you need to know the aspects of them, the definitions of them, and apply them to actual situations. So touching and not moving. So heat transfer with touching and not moving. Convection, also touching, but the objects or the molecules are moving. We often see this with fluids. And by fluids, I mean liquids and gases. The last one that we talked about, radiation, this was the heat that we could feel from the sun. So this is the only one of the 3 where the objects are not touching. So the question asks, which of these forms have the 2 objects not touching? Radiation's our only possible answer. The other 2 are. All right. Number 4, the heat capacity of a substance is referred to as, so this is just definitions again. I highly recommend you just go through and make a list of the definitions from the PowerPoints. You don't have to watch the video. I have the PowerPoints posted with separate slides, so you can just go through the slides and write down the definitions, or have them handy when you take the exam, because you need to look up the definitions of each of these to answer question number 4. So what is temperature? Temperature is the measurement of heat content. So that's not the heat capacity. Specific heat is the correct answer. That is the heat capacity of a substance. It's how much heat is required to raise that substance by 1 degree. So B is your correct answer. C is not the correct answer because latent heat is heat required for a phase change. So you're just using the definitions and picking the correct one based off of the definitions. For number 5, static electricity. So once again, a definition. What is static electricity? That's when we took, and I did an example of it actually during class. I had a balloon and I had some fabric and I rubbed the balloon and fabric together. The reason I was doing this, to cause electrons to transfer, to rub from one to the other. So, which one of these definitions explains what I did? A, B, C, or D?
C.
C. Where there was friction between the balloon and the fabric causing a transfer of electrons. So C is the correct answer for static electricity. For number 6, when you see lightning strike, what are you observing? The lightning strike is actually just caused by static electricity, just on a way, way bigger scale. So when we have the clouds in the air, we have static electricity because the clouds are actually causing friction. There's friction between the clouds, creating some of this static electricity. And then what happens is when the clouds get close to the ground, those electrons that were rubbed off jump to the ground. Okay, so when you see lightning strike, it's really just electrons. So B, electrons. Please don't circle magic. I have to think of 4 choices, so sometimes I just make up a crazy one. All right, let's look at number 7. This is the last concept question, and then we'll work on some of the calculations. The last concept question for a little while, anyway. So here it's electric current. So this is chapter 6. When we talked about electric currents and we talked about different types of circuits, we looked at 2 circuits. We had a series circuit and a parallel circuit. So this is series where we have one after another with our resistors. And then we have parallel. Oops, that was a bad picture, but parallel. So the question is asking, these are the only 2 we talked about. If there are different paths for the electric current to take, what type of circuit are we talking about? Well, it wouldn't be an open circuit, because what they mean by open circuit is where it's not all connected to the voltage source. So if we had an open circuit, what would happen is no current could travel, because there'd be a break in the path and it wouldn't be possible. So open circuit would not be the correct answer. So looking at series versus parallel, the current, or those electrons, are going in a series from one resistor to another. So notice in a series, this red line I'm drawing representing the current, it's the same current going all the way around. But in parallel, once it gets here, the current's going to split, thus taking different paths. So parallel would be the answer for that, because it splits. All right, let's do some calculations now. I'll leave those pictures up because the next 2 questions are involving those pictures, because the number 8 is asking for total resistance if we have a series, so one like this, and they are placed, I have a 5, a 3, and a 7 ohm. Okay, so we look at our equation sheet now. When it asks for total resistance, we have two equations, one for a series, one for a parallel. So writing the series equation down, my R total, I simply add the three resistors together. So in this case, it would be R1 plus R2 plus R3. I already forgot the numbers. There's a 7 ohm, a 3 ohm, and a 5 ohm?
Yes.
Adding them up, 7 plus 3 plus 5 gives me 15. So the series is the easy one, or easier one, I should say, not necessarily easy. The parallel is a little bit more difficult because there's an extra step that you have there. So number 9 is saying do the same thing, but now place these three resistors, R1, R2, R3, in parallel instead. So we go find our R total equation for a parallel circuit, and that is 1 over R total. And we're going to plug in our 7, our 3, and our 5. So that's what this one's going to look like. Now, when we add these together, whatever answer we get, that is not our R total, okay? So if I add these, do I have my calculator here? 1, 7. So I get 0.676. Notice, if I round this, that's one of the answers. That is not the correct answer though. A is not the correct answer because what this value is, this is 1 over R total. So I need to take the inverse of that. I need to press that X minus 1 button on my calculator. If you don't have an X minus 1 button on your calculator, look at this number as a fraction. 0.68 is the same as if I said 0.68 over 1. So when I say take the inverse, I mean flip that fraction. So put the 1 on top and the 0.68 on bottom, and that will give you your R total. It should be 1.47, is that correct?
Yes.
So the actual answer is B. This is the most common one I see people, students get wrong, just because their initial calculation gives them an answer that they see and they just stop. But this isn't, you're not done yet. You need to flip that fraction, do the inverse. All right. Now let's look at some heat problems. That's actually the lab that is due this week. It's using the heat calculation. That's not due this week, it's the one that we're doing this week. So number 10, gold has a specific heat of 0.31 calories, gives all the units. So this is one of those where you're using the heat equation whenever you see heat. Remember there are two equations. They are the same thing, it's just one has two temperatures in it, and one just has the total change in temperature. So when it gives a specific heat is that C value. So that's 0.031. They're saying calculate the heat required to raise the temperature of 20 grams. So 20 grams is going to be my M, my mass. And then they give me two temperatures this time. So that means I have a final and an initial. And it's my job to figure out which one of those two is the final, which one's the initial. So they're saying they're raising the temperature from 22 up to 85. So which one's the final?
85.
85, where they ended. So that means my 22 is going to be the initial. So this is going to give me a positive Q value. So if heat is added, this is a concept that you might want to remember, you're going to get a positive Q value. If the object cools down, or heat is released, taken away, you're going to get a negative Q value. So that's just a way to kind of check, because you'll notice that I give both the positive and negative answers. So you need to know if it should be positive or negative. If you labeled your final temperature correctly, it'll automatically do that for you. But it's just a good check. So what I'm expecting right now, since the temperature increased, since heat was added, the object heated up, I should get a positive number. So when I plug in my mass at 20, my specific heat at 0.031, and then 85 minus 22. And because of that subtraction, I will get a positive Q. Well, I guess that's going to have to be 39, because I can't see those numbers adding up to 1260. So 39, and then the units are calories. Now the next one is using the same equation. This time they're rearranging it for mass. So I want you to go ahead, we're going to skip that one just because I'm not going to ask you to rearrange it for mass. So why show you why show you how to when you're not going to need to know how to do it? Okay, I did ask that question last semester, but that's changed. So we're going to skip 11. And we're going to move down to 12. So for number 12, it's conversion problems now. So we're doing temperature conversions for the next few problems. And you'll see at least 4 temperature conversions on the exam. So make sure you know how to use those equations. So we have 32 degrees Fahrenheit, and we're going to Celsius, correct? Yes. So to figure that out, look at your equation sheet. You want to pick the one that has Fahrenheit and Celsius in it, but also, since you're solving for Celsius, pick the one where Celsius is equal to, because that way you won't have to rearrange it. And that's going to be Fahrenheit minus 32 divided by 1.8. Make sure that you do that top portion first, okay, so in parentheses. Because otherwise, if you don't put it in parentheses, it's going to do 32 divided by 1.8 first. So plugging in, 32 minus 32 gives me 0. 0 divided by anything is just 0. So this actually makes sense because 32 degrees Fahrenheit, if you remember, that's the freezing point of water. Well, 0 degrees Celsius is also the freezing point of water. So it makes sense. Let's do the next one. We have 7 degrees Fahrenheit, and we're going to Kelvin. So this is the hardest type you'll see because you can't go directly from Fahrenheit to Kelvin. You have to go to Celsius first. So Celsius, and then I'm going to go to Kelvin. So if you're trying to figure out Celsius, just like over here, we went from Fahrenheit to Celsius, so we're going to use the same equation. Take the Fahrenheit minus 32 and divide it by 1.8. So plugging in 7 this time. 7 minus 32, so we're going to get a negative number. This one.
Negative 13.8.
So then you take this negative 13.8 degrees Celsius, and since you need to go to Kelvin, you're going to plug it into the Kelvin equation. So you're adding 273 to it. correct answer I have anyway. It's 259.1, I hope that's correct.
Yes.
That's what's on the answer key I provided. So if it's not, I need to change the answer key. So negative 13.8 plus 273 equals 259.1. Or close to it. It would be 259.2, I guess. You always want to pick just the closest one to what you get on your calculator. Depending on where people round as they're doing all the steps, you might get a slightly different answer. But the answers will all be far enough apart that you'll be able to pick the correct one closest to your answer. All right, let's do 45 degrees Celsius to Fahrenheit. So since we're going to Fahrenheit this time, pick the equation where Fahrenheit is equal to. And that's that 1.8 Celsius plus 32. Plug in your 45. A very large number, 100 and something, I'm assuming?
Yes.
113. So you would pick the closest choice out of the ones would be C, 113. Let's do one more. So looking at number 15, they give you a negative number this time, so just take into account the negative. Because I know I do give you a negative temperature and ask you to convert that. Some people find this a little tricky, just because of the negative sign. So Fahrenheit to Celsius, pick the equation where Celsius is equal to. You get Fahrenheit minus 32 over 1.8. So this negative 15, we're taking negative 15 minus 32. So whenever you subtract two negatives, you're actually, it's the same as adding the opposite. So it's going to be adding those two negatives together and then dividing by 1.8. So, negative 26?
Yes.
So I know that was a lot of different temperature conversions, but I know there's at least 4 on the exam is why I wanted to show each type you would possibly see. Okay, so now we're getting into more concept questions. If two opposite charged particles are close to each other, what can we say about the forces between them? So opposite charges, do opposites repel or do they attract?
Attract.
Attract. So it would be B. There's an attractive force. Opposites attract like repel. So just pay attention to the words. For number 17, the north pole of a magnet is attracted to. So this is that compass problem that we talked about in detail. And we have the Earth's core is like a magnet. So the geographical north is actually the magnetic south. The magnetic north is actually the geographical south. So that's, this picture diagram is going to help you with this question. So if we have a north pole of a magnet, it's going to be attracted to what? Well, the north pole of a magnet is going to be attracted to the opposite pole, the south pole. So A, yes, it will be attracted to the south pole of another magnet. But don't just circle that and be done. Look at the other choices. So we always have north ends. North, north. So what A is saying, will the north be attracted to the south pole of another magnet? Yes. Opposites attract. So that's true. For B, the Earth's magnetic south pole, so this is the magnetic south pole, that core, is attracted to the north pole of a magnet? Yes, because opposites attract. So B is correct. Will the north pole of a magnet be attracted to Earth's geographical north pole? Yes, because Earth's geographical north pole is its magnetic south and opposites attract. So all of the above is the answer for that one, because north pole of a magnet is attracted to the south pole of another magnet. But the north pole of a magnet is also attracted to the Earth's magnetic south pole, because they're opposite. And since the Earth's magnetic south pole is its geographical north pole, so all of them are true, all of the above. I've erased my series circuit already, but number 18, in a series circuit, what is constant? Remember, series was where we had one after another. So just to remind you, so in a series circuit, the voltage is additive. The current, remember, it's the same current going through each one of the resistors, so the current is constant. And the resistors, these R's, are additive as well. We see that with, I spelled additive wrong, with our R total equation. We take R1 plus R2, dot, dot, dot. So these are the important characteristics to know with a series circuit. And they will also help you answer not only this question, but other concept questions with the series circuit. So in this case, they're saying which one's constant out of voltage, current, resistance. It's going to be current, because voltage is additive and resistance is additive as well. Power, we don't know anything about power, and the series circuit in this class we haven't learned anything about, but it's not going to be constant. So to increase current, so to increase the amount of electrons flowing through, what are some things you can do? Okay, you decrease resistance, increase voltage. So let's look at this. So here's our voltage source. If I increase the voltage, get a bigger battery, is that going to increase my current?
Yes.
Absolutely, yes. So increasing voltage will help. Decreasing resistance. So if I take out some of these resistors, is that going to help my current? So what resistors are, and when, if you watch the PowerPoint video, I explained them sort of like clogs in a pipe. And you have water being the current, rushing through. Okay, so the resistors are the clogs. Once the current reaches the resistor, it takes a little while for it to get through. So if I take out some of the clogs, do you think the water is going to run faster?
Yes.
Yes. So if I take out the resistors, will the current increase?
Yes.
Yes. So C is the correct answer, both A and B. If I take out the resistors, if I take out the clogs, the current's going to run faster, increase. If I increase my voltage source, my battery, I'm adding more electrons in that current, making that current increase as well. All right, the rest are calculation questions. So there's only 23 here. There is 40 on your homework. Look at all those practice problems that we did in the videos. And I have them posted. If you don't want to watch the videos and you just want to work through the problems themselves, that's fine as well. But if you know all of those and this, you're gonna do good on the exam. So, all right, 20. 5-volt battery is connected to a toy car. The current running through the toy car. So this is our knowns and unknowns. This is our typical physics problems that we've been doing this whole semester. Okay, so if we see 5 volts, let's associate it with a variable. B, that's the easy one. The 2.3 ohm resistance. Well, it tells us that 2.3 ohms is a resistance. So that's our R value. The current running through the toy. Now this is the hard one, knowing what variable current is, but that's why I basically gave you a cheat sheet on it. When you look at the cheat sheet, it tells you current in amps and that it's I. Okay, so use that, have your equation sheet ready. That's our question mark. So the equation we have to solve for this is V is equal to IR. Rearrange to solve for the current, for the I. We want to get rid of the R, so we divide by R. Whatever we do to one side of the equation, we have to do to the other. I kind of went through that rearrangement quickly, but I feel like we've done it a whole bunch of times. So now we plug in, our voltage is 5, our resistance is 2.3. The only thing close to that on here I think would be A, 2.2. See, I can't calculate this stuff in my head, but if you give me choices, I can usually pick out what the answer would be. Or the closest answer. That would be A. All right. Number 21, the current running through a microwave plugged into an electrical outlet is. All right, so let's start with that 1.2 kilowatts. Watts is what? Units for power, yes, so that's our P. Volts is V, that's the easy one. Units are the same as the variable. And they're asking for current. That's what the first part of the question said. The current is question mark. All right, so the equation we have with these variables is power is equal to voltage times current. But what does power have to be in when we use it all the time in every chapter we've done? Can it be in kilowatts?
No.
It has to be in watts. Okay, so this is where a conversion is important. So we need to convert it. And it's actually metric to metric, so it's not too bad. Because K is kilowatts, so we're at the K. And what we're trying to get is to watts, and that's our base. That's the middle. That's what goes in that empty space. So we're at the K, we want to get to the W, so we move it 1, 2, 3 times. What direction?
Right.
To the right. So start at the decimal, 1, 2, 3. So what's going to go in those empty spaces?
0.
0, so we get 1200 watts is our power. So this is the value we want to plug into the equation. First I'm going to rearrange it though, to solve for current, to solve for I. So if I want I by itself, I need to get rid of the V, so I divide by V. Whatever I do to one side of the equation, I have to do to the other. So I get current is power over voltage. So 1200, so 1 in watts, divided by 110. See, 10.9. So if you didn't convert this first, you would have probably picked A, 0.011. That's what would have changed there. So I do give plausible answers if you forget to do a conversion. So just make sure you're paying attention to your units. I don't ask you to do a conversion very often for very many of the problems, but I do it sometimes, so be aware of that. All right, number 22 is asking about energy. We have a 3.5 watt charger. So watts, once again, we just said it, is a power. Okay, how much energy does a 3.5 watt charger use to charge your phone for 45 minutes? So 45 minutes is a T, a time. And energy is what we're looking for. What is energy? Power times time? The only energy equation we have in these two chapters is is electrical energy, power times time. So when we use this equation, we need power in watts. What do we need time in? We need time in seconds. It's in minutes. How do I get it in seconds? I'm going to convert. So how many seconds are in 1 minute? 60. So if I multiply by 60, because 1 minute is equal to 60 seconds, this is our dimensional analysis. So to get from minutes to seconds, you just multiply by 60. And what do you get for that? I can't do that in my head.
2,700.
2,700, thank you. Now this number is what I want to plug in to the equation. So I don't even have to rearrange. I just plug in my 3.5 and my 2,700. Was it 9,000?
Yes.
450 joules? 9450 joules. Right. And do one more, and then I want to talk quickly about another type of problem that's going to be on there. And that should be it for the review. So the last one, 23, vacuum with 40 amps of current. So 40 amps. Amps is what? Current, so it's I. It's connected to a 110 volt circuit. Calculate the resistance. So it's calculating R, question mark. So we're back to our V equals IR equation. So if you look through your equations, the only one that has those three variables is this one. We're solving for R this time, so we want R by itself. So I need to get rid of the I. To get rid of I divide by I. Making sure to do that on both sides. My I cancels, leaving R by itself. And to solve for R, I get voltage divided by current. So 110 divided by 40. The only thing remotely close to that would be 2.75. The other numbers are huge. So one problem that wasn't on here, but is on the exam, is the cost calculation one that we did last week. Where you have the 3 steps, and you have to convert kilowatts, and then calculate kilowatt hour, and then the total cost. So these steps are all on your equation sheet, so that's why I didn't write them out in detail. But make sure you know how to do this one. Okay, we did it last week. It's on the practice problems that I have posted. So try it again and make sure you understand the steps and can calculate that one out. Because there is one of those on there. But otherwise, I think we covered pretty much every type you're going to see. And most of the concepts. So look at the practice exam that we've done just now, but also look at the practice worksheets that we worked through in class. So that is it. So it's a pretty light week. You just have this exam that's due on Sunday. So if you have extra time, I recommend trying to get that paper done, because we're starting chemistry next week, and chemistry most students find a little bit more difficult than this physics stuff. So you might need to take some extra time to focus on the chemistry. So you might want to knock out that paper so you don't have to worry about that.